I actually had kind of hoped to pull up the thing you did last week and go through it together as a class, but I'm not sure we'll have time for that, so we'll just move on. All right. Integral as net change. I believe that when I introduced you to integrals in chapter 5, I told you it was good for you to go ahead and start thinking of integrals in what way?
As net change.
Accumulation, right? The accumulation of whatever the rate represented. Well, how would that be net change? Well, and I'm just going to sketch the first little piece of the first graph that was on that thing you did last week. And it looked something like a square root graph, right? The first little chunk of it. And if I recall, it went from 0 to 5. All right. Well, if this is a rate function, and I told you on that sheet that the pictures I gave you were in fact rate functions, then what would you have to be accumulating? Distance traveled, maybe? That wasn't hard. I didn't ask you to tell me in what units, because obviously if you don't have the units given, you can't specify the units. But you could say in whatever units of distance this thing was written, right? Okay. I do believe I told you that the graph was in minutes. And one of the things you should have noticed about all three graphs was they went from 0 to 17, right? So what would that imply about that commuter? That they allotted 17 minutes. It doesn't take 17 minutes, because remember in the first picture, they got there in 5 minutes, right? Which the group that had the best description, I know, and some of you others might have also added this, but I know for a fact they said this. They said after they'd had this delay and had to turn around and go back, because the first picture was the positive square root graph, right? And then there was a corresponding picture below the x-axis. So, as I was saying about this particular picture, as you might recall it, if you don't, you can pull it out and look at it, because you all got a copy. The first little section looked like 0 to 5 of maybe a square root graph. The second section looked like that same picture flipped upside down. So, on the same interval, right? Same interval length anyway. So, what did that happen net? She's back where she started from, right? Because if I, however far she traveled in those first 5 minutes, seconds, whatever this was, presumably minutes, okay? However far she had traveled in that distance, she had to travel back to have the exact same distance under the x-axis, right? Does that make sense? So that's kind of where we're going with this stuff. All right, well then over to the sides, you had what looked like a parabola upside down, right? And that's where the entire distance was. And what should have happened is that in all three pictures, your total, not your total area, but your net area was equal. And some of you made that happen and some of you didn't. But so what did that say? Well, if they were all 17, from 0 to 17, then that means that the person that the problem was about somehow in their schedule allowed 17 minutes every morning to get to where they were going, right? First morning, didn't go well, right? Had to actually make the trip in 5 minutes, all right? And then the next morning, smooth sailing, she just coasted right in, right? Just a nice, easy ride. Slows down when she gets to where she's going, all that sort of thing. And then the third one, we had a different picture, right? A little parabola-looking thing at the beginning and another one at the end. Well, what would that mean? If both of those pieces on that last picture were above the x-axis, what did that say?
She went fast and stopped for a minute.
Yeah, she went towards her destination and stopped. And then what?
Then kept going.
Then finished her trip to her destination, right? How do we know she never turned around?
Because there was no negative.
Right. But her bicycle was not moving between those two peaks, right? Again, as I mentioned the other day, that does not mean that she was, kidnapped by aliens or, got hit by a truck or I'm trying to remember what some of the other stories were. But so in this particular picture, if this is, let's say that my rate is given in feet per second. And it wasn't and I'm taking this from that sheet, and obviously it wasn't feet per second there. Because that means she would get to work in 17 seconds. You would need a bicycle for that, right? I couldn't get on a bicycle in 17 seconds because I have clips on my pedals. No, I have a road bike. That's how they ride the road bikes. You don't actually.
I don't know what clips are.
Your shoe clips to your pedal.
So wait, what happened?
That's how they can spin so fast.
Yeah, what if you fall and your
You don't. Then you fall with your feet clipped to the bike so you don't fall.
How do you stop? Both your feet.
Well, when you stop, you twist your foot and it unclips, and you can put a foot down. Yeah. Yeah. God, didn't know y'all didn't know that.
It's like failing to bike.
I feel like that would be really like, I don't think I could do that. Like, there.
Do y'all hear the difference in the stupid conversations we have versus my asking you things like, what do we know about 33 over 1393? It's a fraction. I mean, come on. All right, so here we go. Back to this example. All right, so what would this represent if I have one little section that I'm looking at? How would you interpret this based on what you know so far?
She's going really
She's
fast.
traveled that far.
Okay, her rate is increasing. Okay, why is the rate increasing?
Because it's
Okay, where does the rate start? At 0. Why would that make sense if I'm on a bicycle? Because I'm on the bicycle, time starts when I actually start pedaling, right? So I'm going to start from 0 and theoretically go faster up to some degree, right? All right, so the rate is increasing on the first 5 seconds, right? And what else do I know? Think about everything you know about particle motion.
We peak at 5 seconds.
Well, at the maximum rate happens at 5, right? Which has to do with the fact that the rate is increasing over this interval. What else do we know? Particle motion. Come on, guys. Okay. Well, if the rate is increasing, there is an acceleration, a positive acceleration here, right? Okay, that's true. Okay. What did we talk about? Let's talk about particle motion for a minute. Go back and dig that out of your brain. All right. What are the relationships in particle motion? What was the function that told where the object was called? The position function. S of t was our position function, right? And then what does v of t, which is my what? Velocity function. Where does that come from? That's the first derivative of the position function, right? And then we've already talked about acceleration. Where does that come from? That is the derivative of velocity, which could also be described as the second derivative of the position, right? Now, you've talked about velocity. When I ask you what you know about this picture, from this picture, you've talked about velocity, you've talked about acceleration. What have you not talked about? Position. Okay? So, talk to me about where she was versus where she ended.
We moved that distance.
Moved what distance? The area between this curve and the x-axis describes not only how far she traveled, but
How much? Well, how?
in which direction. Yes? Because in velocity, how do we interpret velocity in terms of the particle motion? When the velocity was positive, yes. And when the velocity was negative, moving to the left, yes?
Yeah.
You're horrifying me right now, just so you know. Okay. Do you remember, I'm so scared to ask this, because I was expecting much more animated conversation than we just had. All right, let's talk about the word displacement. And I'm just going to step out on a limb and say, if you didn't know anything I just asked you about, then you probably have no idea what I'm even talking about here.
Oh, that's how you start.
Y'all are muttering like crazy people.
The position graph, so from where it starts, we subtract where we end up from where we start.
S of B minus S of A.
Today is my last day of physical therapy.
That's what this day needed, another interruption. Okay, displacement, we talked about back whatever chapter that was in that we talked about particle motion. displacement was the first idea, okay? Because if I run back and forth 50 times, the displacement hasn't changed, is no bigger than if I only went back and forth once. Does that make sense? Because displacement is simply a description of where you are at an instant relative to where you started. Okay? So what would the displacement be on the picture we just looked at?
That's a 5.
Right. How would I get, well, what would S of 0, well, first of all, what would S be for this picture? What would S of t be? Think like a calculus student. Okay, well, if the velocity is the derivative of the position, and that's what this rate is, it's a velocity,
Okay, so it's.
how do I get,
Antiderivative.
that's right, the integral of r of t dt. Right? Okay, well, let's just go ahead and put a 0 and a 5 there. And that would, what do we call those universally?
Limit the integration.
Limits of integration, but what specifically would I call A? What variable do we use? A, and the upper one is called B. I will take you back to this screen to remind you what we just wrote to the as our definition of displacement, which we learned first semester. You with me so far? About to have a big aha moment here. All right, so if I want to know the displacement, then if I want, and I'm going to write this, and somebody better have something impressive to say to make up for all the fog moments we've had this morning. If I write S of 5 minus S of 0, that is the,
Yes, FTC.
Big F.
that's right, that is big F, that is the FTC, right?
Also big F.
Had a little duet there, right? So in other words, what would I do to get S here?
Take the integral of.
That's right, I'm going to take the integral of the rate function, and then I'm going to plug my limits in, right? Which gives me displacement, right? Good job. All right, so I said a minute ago it wouldn't matter if I walked back and forth, right? So even if we had a section that was under the graph, the net displacement would be the same thing as the actual integral, right? Okay, that's kind of where we're going in this section. I want to call your attention, if your book's not open, that's fine. I'm going to kind of read this to you right quick to explain to you how I said that all of the things we were talking about before we ever started our notes today were related to this. There's a green box on page 386, so you might want to just make yourself a note if your book's not open. And if your book is open, you can look with me. Green box, page 386. I don't necessarily know that it's even worth getting it out, but if you want to, you can. And it's the strategy for modeling with integrals. And now I'm just going to try to squeeze in an example or two if time permits. Step 1 says, approximate what you want to find as a Riemann sum of values. If f of x is the function and the interval is a closed interval from a to b, then you partition the interval into subintervals of length delta x. Approximating the sums will give you the sum of all those areas, right? That's what that notation means. And if you're not looking at the book, it's that delta, it's the sigma notation with the subscripts and the delta in it and all that stuff. We talked about all that back in chapter 5, yes? Okay. Or maybe 6, I don't remember what chapter it was. The approximating sums will give you what? When you add those all together, what does that approximate? The area, which is really, now that you know more than you did when we first talked about it, that's really approximating the what? Integral. Right? Well, then it goes on to tell you in step 2, write a definite integral. Okay? And then the first one we're talking about f of x, and now it's the integral of f of x dx. And then express the limit of these sums as the norms of the partitions, aka find the integral. So if I find, what's the difference between finding the integral and using Riemann sums?
It's an estimate.
Right, Riemann sums are an estimate. Finding the integral is how it relate that back to the Riemann method.
It's more. It's like putting like a ton of little rectangles.
That's right. We had a ton of little rectangles because remember we got more and more accuracy as we added slices. Our slices were thinner, right? So by definition, in the same way that we had the limit definition of the derivative, we have the limit definition here, and now we want an infinite number of rectangles, right? So when you integrate, you're finding the same thing you would if you took the limit of infinite rectangles. Does that make sense? Yes.
On our project, do you want us to include that little box?
Not necessarily. That's just to kind of help you understand why I'm making such a big deal about the rectangular approximation method, and why I was concerned about the errors I saw in that little activity I gave y'all last week. All right. We're not going to do the work section of this lesson. I'm sorry, I shouldn't have said that. It's actually a section in your book called work. And it has to do with physics. So we're going to kind of leave that alone. It has Hooke's law in it, so you shouldn't see that. I'm going to see if I can't squeeze in a little example here. And to me, these are kind of baby examples. So let's go with number 2, an even numbered one, to see how all this works. Because this is another one of those where our notes would be very theoretical, but the application is pretty straightforward. So this should be an easy section to knock out and move on to the big stuff in this chapter. Big stuff in terms of complexity and having to understand and process. And our v of t on number 2 is given as 6 sine 3t, and our interval is from 0 to pi halves. Now I will also tell you, and I'm going to do close bracket, they use the inequality notation. I'm also going to tell you that on your test you took a bigger hit for your trig errors than you have in the past, because the closer we get to the AP exam and you're still making them, the worse that problem is. Like if you don't know that the sine of pi halves is 1, we have a problem. We need to know our unit circle, okay? And these are no calculator questions, aren't they, when they're gray bubbles? Isn't that the way this book works? Okay. A says, well, actually, let me read you the previous part. The function v of t is the velocity in meters per second of a particle moving along the x-axis. So we should jot that down, meters per second. Use analytic methods to do each of the following. Analytic means show the freaking steps. A, determine when the particle is moving to the right, to the left, and stop. Does this sound familiar? Okay. Okay, well, if I want to know, and you really need to, because this is where you start getting dropped off in the middle of the problem, where when we first learned it, we got the position function and worked our way down through the others. Now you might be given the acceleration and be asked about position. Okay? So, having said that, if I want to know when a particle is moving to the right, left, or stopped, what do I need to think about? Velocity. So what is that? It's what they gave me, right? So what do I do? What do I need to know about it? Find our zeros, okay? So we're going to do a dangram for our v of t. And we're only going from 0 to pi halves. So we're in the first quadrant, right? All right, but now we have to be careful because of the 3. Because something in your brain says, well, if we're in the first quadrant, it's all positive, right? Okay, but you have to be careful because of that coefficient on the inside. So let's come over here and use theta. Now, we're stepping aside and using theta because that is a universal symbol for the angle, okay? What is my angle when sine is 0? Okay, we know it happens at 0, right? Which is one of our endpoints, so that takes care of that, right? Where it happened again? At pi. And when would it happen again? 2 pi. Right? Okay? So, as it turns out, if I plug any of those values in, or not plug them in, but now I'm gonna work with those and put ellipses at the end, because obviously this would go on every pi I go to the right or left, I'm going to be at 0 for sine, right, for the angles. All right, so now you got to realize that theta in this problem is 3t. So if 3t is 0, that implies that t is 0, right? Already taken care of by my chart. Are you with me? Okay, and then if 3t is pi, what's t? Pi thirds. Is that in there? Yeah, it is, isn't it? Okay, so I'm going to go ahead and stick that in there. And it doesn't really matter proportionally where you put it on your chart. Just know that it's in the interval. Okay, and we'll come back and finish this in a second. Let's go one more. All right, if 3t is 2 pi, where am I? 2 pi thirds, right? Okay, is that in there? No, so we don't care about that one. You with me? That's the way to think about it. So we've taken care of all, the only time it's 0 in this interval now. You with me?
Because you gotta multiply it by 3.
Because it's not just the sine of t, it's the sine of 3t. What does 3 do to a graph inside the function? It pulls it back to the y-axis.
Oh, yeah, because it's on.
So it takes your sine graph and squeezes it back to the y-axis. So you're going to be 0 earlier than pi now. You're going to be 0 at pi thirds. Because when I plug in pi thirds, don't I get pi? Which is 0? Are you with me? Okay.
Mister, couldn't you just make your diagram from 0 to 3 pi halves?
No. Because the diagram needs to represent the variable in the problem, which is t, not theta. And that's the important distinction to make about trig. Okay? All right, so between 0 and pi thirds, give me a reference angle you know. Pi 6, I'll take that. All right, that's the first angle, right? Okay, well, if I put pi 6 into this function, what angle, or what am I taking the sine of? Pi halves, which is 1, which is positive. Right? And then, if I pick an angle bigger than pi thirds, okay, well, let's just think about it, all right? Well, let's say it was 5 pi 6. No, that's too much. We're at half.
Yeah. It's not number between, so we have to choose.
No, 3 pi fourths is too big. It's not, you're not going to have one you know. So think of a fraction that's between 1/3 and 1/2. 4 pi tenths. 2 pi fifths. Okay? So if I did that, I would be at, put the 3 on it. If I have 2 pi fifths, that'd be 6 pi fifths. Where is that? 6 over 5 is bigger than 1, right? So that gets me out of the top half of the circle, right? Into the third quadrant. What is sign there? Negative. Not to mention, if I'm thinking function transformations and it squeezed it, wouldn't, because you already know that sine looks like this for its first period. Well, if it cuts it down to 1/3 of that, that means I've got an entire cycle in there. If I figured out where the velocity is equal to 0, don't I know that if it's positive here, if that's all it did was squeeze it, it's positive and then negative? You've got a lot of background information in your heads, or supposedly, that would help you think about this problem. And we will pick up with this first thing tomorrow, and then you should have time to work